Hi everyone! For this video, we are about to learn the concepts that governs our topic for today. This is the orders of chemical reaction. In chemical kinetics, the order of reaction with respect to a given substance is defined as the index or exponent to which its concentration term in the rate equation is raised. For the typical rate equation of form, R is equal to constant multiplied to the concentration of the first substance raised to its coefficient and then multiplied to another concentration in the substance raised to its coefficient again. So to start with, let us define the three orders of chemical reaction. First is the zero order. It is independent of the reactant's concentration. The rate law expression is where rate is equal to K sub O in meter per second units. Concentration time equation is the initial concentration minus the concentration equal to K sub O multiplied to time. For the half-life equation, it is equal to the initial concentration divided by 2 multiplied to constant sub O. And for the graphical plot, we can see that the concentration of A is relative to time. Next is the first order. It depends on a single reactant with exponent equal to 1. Its initial rate of reaction doubles when the reactant is also doubled. Rate law expression is where rate is equal to K sub 1 or the concentration of A is raised to exponent 1. Concentration time equation is the logarithm of initial concentration divided by the concentration equal to constant multiplied to time divided by 2.303. The half-life equation is equal to 0.693 divided by the constant, and for the graphical plot, the logarithm of A is relative to time. Lastly, the second order. The rate of this reaction may be proportional to 1 concentration squared. Its initial rate of reaction quadruples when the reaction is doubled. The rate law expression is where rate is equal to K sub 2 or the concentration is raised to exponent 2. Concentration time equation is when 1 divided by the concentration is equal to constant multiplied to time plus 1 divided by the initial concentration. The half-life equation is equal to 1 divided by the constant sub 2 multiplied to the initial concentration. And lastly, for the graphical plot, we can see that 1 divided by the concentration is relative to time. With these equations enlisted below, these are the governing principles of the orders of chemical reaction. So to sum up our lesson today, this is a table of the corresponding equations per orders of the chemical reaction. Let's start with the zero order. The rate law expression of this order is where K is equal to negative concentration divided by the time. For integrated law expression, the concentration is equal to the initial concentration minus the constant multiplied to time. The units of K is meter per second. For the linear plot, concentration is relative to time, and for the half-life, it is equal to the initial concentration divided by 2 multiplied to K. Next is the first order. The rate law expression of this order is where K is equal to negative concentration divided by time, which is also equal to the rate law expression of the zero order. Next is the integrated rate law expression. It is where the concentration is equal to the initial concentration multiplied to the Euler's number raised to negative K multiplied to time. The units of K is 1 per second. Linear plot of this order is where the ln of the concentration A is relative to time. The half-life of this order is when the ln of 2 is equal to K. For the second order, the rate law expression is also equal to the first and zero orders. It is where K is equal to the negative concentration of A divided by time. The integrated rate law expression of this order is when 1 over concentration is equal to 1 over initial concentration plus constant multiplied to time. The units of K is 1 per meter second. The linear plot is where 1 divided by the concentration is relative to time. The half-life of this order is when 1 divided by the constant multiplied to initial concentration. And lastly, for an additional concept, the nth order. The rate law expression, the integrated law expression, the units of k, the linear plot, and the half-life expression of this order generalizes the zero, the first, and the second order of our chemical reaction. Now that these terminologies are defined, let us learn how to identify the rate law expressions by incorporating these concepts. Given the data below, find the rate law for the following reaction at 300 Kelvin and the corresponding rate constant, given A plus B directed to C plus D. For trial 1, the initial concentration of A equal to 1, the initial concentration of B equal to 1, and the R initial concentration is 2. For trial 2, the initial concentration of A is 1, the initial concentration of B is 2, and the R initial concentration is 8.1. For trial 3, the initial concentration of A is 2, and the initial concentration of B is 2, and the R initial concentration of 15.9. In order for us to identify the order for Y, we should use trial 1 and trial 2. Given that the general formula for the rate law expression is equal to the constant multiplied to the initial concentration raised to x multiplied to the initial concentration of b raised to y. Since we're going to use trial 1 and trial 2, we're going to use their rate law expressions. Given the r sub 2 is equal to constant multiplied to 1 raised to x multiplied to 2 raised to y. Next is the rate sub 1, which is equal to k multiplied to 1 raised to x and 1 raised to y. Canceling out all the possible cancellations for this algebraic equations, we're going to get y is equal to order of 2. Next is for the order of x. Using the process of how we got the order of reaction for y, we're going to use trial 2 and trial 3. Using their respective rate law expressions, we're going to get the order of reaction for x, that is 1. In order for us to calculate the value for the constant, we're going to derive its formula using the general form of the rate law expression. We now get constant is equal to the rate divided by the initial concentration of A raised to x multiplied the initial concentration of B raised to y. Substituting all the values we got a while back, we now get the constant value, which is 2 meter raised to negative 2 multiplied to second raised to negative 1. That ends our lesson for today. Hope you understand our topic